Hi everyone, welcome back to Toronto Workshop. Guest this week is Apoorva Lal from Netflix. He's going to talk about modern balancing methods for causal inference. He's a data scientist on the experimentation team at Netflix, and he works on observational causal inference with spatial and panel data. He's got a PhD from Stanford, which is where the work that he's going to talk about was done. And so thank you very much.
Great. Thanks, Rohan. Thank you all for the invite and thank you for coming. So I'm going to talk about work that I did during my during graduate school for the most part. I'm on the experimentation team now, and I work on like a variety of causal inference related tasks. And this work basically focuses on what I call modern balancing methods. And what that means is like it tries to integrate insights from machine learning into causal inference, which has been a big theme in the causal inference literature in the last decade. So the outline of the talk is I'm going to introduce the problem. I'll give you, this is very much a framework style paper, so I'm going to cast a bunch of analyses that folks tend to do in a common framework. And then I'm going to talk about lots of simulation studies that I might or might not get to or might speed through. But the goal here is to basically cast a lot of things in a form that is amenable to a sort of the application of optimization and machine learning. So that's where I'm going to spend the bulk of my time. And I'm happy to take questions during, so because there'll be a fair amount of notation. I think you'd be doing the room a favor if you ask questions about notation. So please don't hesitate to do that. Cool. So the basic pitch of the project is to sort of notice that there's been an explosion of methods in observational causal inference in the last decade, and a lot of them aim to weaken identification assumptions and relax functional form assumptions, and also estimate potentially new quantities, although that's not going to be the goal here. The key insight driving a lot of these innovations have been the separation of identification and estimation. So causal inference is fundamentally a missing data problem, which means you need to make a certain set of assumptions to identify the missing data from your observable data. So once the identification is done, the second step is usually estimation. And the estimation step is a curve fitting problem. And then there's no reason for us to restrict ourselves to using linear regression or logistic regression. You can use anything that fits the data well, given that you've identified a way to estimate the parameter that you actually care about. So the most popular of these ideas is this now celebrated notion of double machine learning, which hinges on this sort of possibly the most popular form of observational causal inference, which is the notion of selection on observables, which basically hinges on the treatment being as good as randomly assigned, conditional on a set of observed covariates. Now, that's a pretty strong assumption. I think in general, in social sciences, people are pretty skeptical of this assumption, which is why I think this has taken off in very data-rich settings in industry more so than it has in, say, like an economics department. But one of the claims I'm going to make to you is that with repeated measurements, we can relax this using difference and differences and synthetic controls. So a huge part of the modern sort of social scientist toolkit is to use repeated measurements in ways that relax this incredibly strong, as good as randomly assigned assumption. So the goal of this paper is to express many popular estimators in this category in a shared augmented balancing form, and provide you with extensive simulation studies and empirical to guide empirical practice and software that's currently cooking. This is complementary to some very useful papers that have come out of Berkeley recently. So Avi Feller's group has a series of papers that basically show this augmented IPW type structure applies in a bunch of settings. So this is very complementary to that work. Cool. So the framework, this is where I'm going to throw a lot of notation at you, and I would appreciate questions if there are any confusions. So I'm going to focus on a very particular estimand here. And by estimand, I mean the thing that we want to estimate. So the estimand is the notion of estimator and estimand. The distinction typically boils down to The estimand is defined in terms of observed and missing quantities, and estimators have to always involve observed quantities. So the bulk of the work in causal inference is how to get from the estimand to the estimator. With that out of the way, here's what you would observe in a typical data analysis setting. You would observe an outcome, which is a real number, a treatment, which is going to be binary for the purposes of this talk, but the generalization is not without loss of generality, but I think there are analogs to the continuous treatment setting, and a treatment vector that lives in this d-dimensional space of R. And there are corresponding covariate distributions, which I'm going to call curly T and curly C for treatment and control units. So the most standard estimand in causal inference is the average treatment effect, which is the average difference between two potential outcomes under treatment and under control. The potential outcomes are treated as fixed. So every unit has counterfactual outcomes under each intervention, and we can sort of combine them, C-bind them together, and that would be called the science table in Don Rubin's framework. So if you have the setting that you can identify the entire science table, you can target the ATE, but a much more feasible estimand is the ATT, which is basically this same difference, but conditioning on the observed treatment assignment. So this is basically conceding that people sort into taking the treatment for reasons that are unobserved to the econometrician. And the goal is to say something useful about the people who took the treatment because they took it for reasons that you can't observe. And these two are very popular estimands, obviously, and they require related but distinct identification assumptions. So ATE requires positive treatment probability for all units, which might not be true for a lot of things. This is just not very credible, and ATT therefore is a compromise, like I said, where we condition on the realized treatment assignment and construct counterfactual potential outcomes in the absence of treatment for the treatment units. And what that does, I got my fancy laser pointer here, is that we have two things to estimate, and one we can estimate very easily. We can estimate the sample mean of the potential outcome under treatment for the treated units. This is a sample mean. So the curve fitting problem now is to estimate the counterfactual mean in the absence of treatment for the same treated units, which is this counterfactual mean, which I'm going to call C hat for the rest of the talk. So now that so in each sort of design setting, we're going to talk about what we need to be able to consistently estimate this C hat and how to estimate it well. So this introduces this notion of balance. So balancing weights are this usually quite theoretical quantity. And the nice thing about them is that they can be used to construct this counterfactual mean in a very straightforward way. So the standard inverse weighting style estimator that we've known about since the middle of the 20th century basically says you can reweight the distribution of the outcomes, and the weights are going to take the form of a density ratio, dt over dc. And then you average that over the control units, and then you have a good estimate of the counterfactual mean. The problem here is that this density ratio is quite challenging to estimate using plug-in estimation, and I'll define what plug-in estimation is in a second. So usually the standard practice that we would learn in early stats classes is basically fit a propensity score. So you fit a logistic regression, for example, of the treatment dummy on covariates, and then plug in those estimates that come out of this, the pi hats, to construct an inverse propensity score with pi over 1 minus pi. So this works well in very large data sets when the propensity score is correctly specified, but this could be arbitrarily bad if your model is bad. So because this is a ratio, this inversion step can inflate even small errors in estimation. Therefore, a lot of work in the last decade has basically focused on estimating this indirectly. Or you could actually flip the labels and think about this as like the propensity score approach was this somewhat indirect procedure where like you estimate a classification model and then you plug it in to construct this density ratio. The alternative framing is you directly estimate weights to minimize covariate imbalance between the treatment and control groups. So this is the sort of automatic estimation of Risch representer literature. So in general, this literature basically takes balance as the goal, because balance is what you want in doing observational causal inference. So stating this as a directly estimate ways to minimize balance problem should immediately make it seem like we're going to be doing optimization, and that's what we're going to be doing. So here's a constrained optimization problem, which says I want to minimize imbalance or maximize balance subject to the weights being proper. And I also want weights to be as less dispersed as possible. So I don't want too much dispersion, because very extreme weights can screw up my estimation. So this constrained optimization problem is somewhat complicated to solve, but the nice thing about stating it as a convex optimization problem is that we can use duality theory. So for convex loss functions, the dual is much easier to solve using a regularized propensity score. So this sort of takes the structure of a logistic regression again, but the regularization is going to guard us against the problems that came up when we used like standard logistic regression, for example. And this has much better finite sample properties, which I'll try to convince you of with simulations in a second. So now that we've defined our weights, we're going to use these weights repeatedly in different settings. So in the cross-sectional setting, I've already talked about briefly, we are going to rely on the standard Sutva assumption, which is not innocuous again. You could be in settings where spillovers are so widespread that this assumption that my treatment only affects my outcome is not credible, in which case you're in a very different domain of causal inference. That's beyond the scope of the talk today, but most observational methods tend to assume Sutva and then make additional assumptions to identify what they want. So we are going to assume the same, a slightly weaker version of the as good as randomly assigned assumption on confoundedness. And we're going to assume that treatment is not completely deterministic. So for any given covariate vector, you can have units that have propensity score equal to 0, because it just makes no sense for said units to take up the treatment, but we can't have units taking treatment with probability 1, which again, might or might not be credible, which is why we're going to try to move away from cross-sectional settings in a second. And just for notation, I'm going to define the sample mean of the treatment as rho hat. So once I've set this up, there are like 3 standard ways that you can construct these counterfactual mean estimators. One is a regression. You basically fit a model on the control units, and then you use R's predict function or Python's predict function, and then you predict it over the treatment units. Average that, you get a potentially good estimate of the counterfactual mean. We could also do the reweighting approach that I mentioned earlier. And the approach that has the nicest robustness properties is what are now known, thanks to the double machine learning literature, as doubly robust estimators. This idea goes back to the 90s, but the basic guarantee from this kind of estimator structure is that if your regression is good or your weights are good, you're good. So basically, this gives us 2 shots at getting the functional form right, which paired with very flexible estimation strategies that come from machine learning gives us a lot more confidence in the estimates that you would get from this reweighting estimator. So this takes the form of a regression and a reweighted set of residuals. So if there are mistakes in the regression function, the weights will correct for them. And if the weights are good, the regression piece kind of goes away. So that's what sort of makes this adaptive between these 2 previous strategies. And it's a rule that when you give an econometrics talk, you show Lalonde. So here's to show like progress in causal inference. I think the famous Lalonde 1986 result is that observational methods weren't very good at recovering the experimental estimates. So, but that has changed. So in this case, I've outlined the experimental estimate in this dotted line. And when you apply observational methods to the experimental estimate, because the treatment is randomized, we shouldn't expect the estimates to be all that different. And when we use observational data, and this is particularly challenging observational data for the Lalonde setting. The findings in the original Lalonde paper was that the estimates were way off because they were using relatively simple adjustment methods that didn't adapt to the data. When we use our preferred estimators, for example, like augmented balancing style estimators, we tend to do pretty well in recovering the experimental estimate. So the most notation heavy slide in my talk, which I'll skate over very quickly, is if you want to think about the formal properties of this estimator, the way to think about it is to just write down the bias of the estimator. So the weighting estimator has a certain bias, which involves the true regression function, while the augmented balancing estimator has a bias that involves the residuals from the outcome function. So in general, if your outcome model is not totally garbage, your regression error, this blue thing, is going to tend to be smaller than the error that comes from not directly estimating this red thing. So regression error is easier to balance than the unknown regression function, and therefore this light blue piece, which is our outcome model, and the weights tend to play complementary roles. So regression can soak up the strong components in the data, and the weights can pick up the weak ones. So in general, the latter has better performance, and that's kind of shown by this Brunsmith paper. And the nice thing about recent insights has been to realize that I think in certain settings, these actually collapse. So there's a way to write the second estimator as a single ridge regression. And that's a very interesting numerical result. I'd recommend looking at it. So one implication of that paper is that they should be in different bases. So, but balancing score and outcome models are both machine learning models, but if one is linear, maybe the other one should be a tree, for example. So that would pick up the two different ways that the data model could operate. And there's a good standard error estimator. Okay, now let's move on to a difference in differences setting. So this figure should be somewhat familiar to people who have done this kind of work in the past. We observe 2 periods, and in the second period, one of the units is treated. This could be an aggregated data set, but in the sort of seminal example of this was, for example, restaurants in New Jersey and Pennsylvania, and I think it was New Jersey that had a minimum wage. So this kind of setting basically allows us to relax the assumptions that we had in the previous setting, the purely cross-sectional setting. So as a motivation for this, unconfoundedness is simply not credible in a lot of settings. So we want to allow for level differences in the untreated potential outcome across treatment and control due to unobserved factors that we simply do not observe. So in that case, standard unconfoundedness estimators do not give us point identification. But if we have 2 periods of data, we can make progress. So in this case, we have the outcome measured in period 1, the outcome measured in period 0, the treatment, which applies only in the second period for a subset of units, and a covariate vector. So an estimator for the counterfactual mean that we want to construct is the untreated potential outcome in the, this is the Estimands, this is a typo. So the Estimand is the counterfactual mean in the absence of treatment for treated units in second period. That's a mouthful. It'll get worse. Sorry. The identification assumptions that we tend to make in this setting is basically no anticipation and parallel trends. So this is easier to see in a picture. So basically, if we assume that the 2 sets of units were going to have the same trajectory in the absence of the treatment, we can then and we are allowing for the fact that the untreated units and treated units have level differences. So this would have meant that we would make no progress in the purely observational setting because the control units and treatment units are so different that their propensity scores would be 0 or 1. But in the presence of multiple time periods of data, we can allow for these level differences, but assert that if these gaps are stable over time, the remaining gap that we get is a causal effect. That's broadly what parallel trends asserts. And we can do this conditional on covariates. This might seem somewhat strong, and I agree that it is. This is very hard to verify in the two-period setting because you can't see time periods going back whether these two groups tended to co-move. So that's where we're going to be going next. So for estimation in this difference in differences setting, the standard estimation strategy is to take the baseline outcome for the treatment and then rescale it, like add this trend for control piece. And so that's going to be take this point and then estimate the trend from the untreated units and then scale this up. And this is your counterfactual outcome. So we're filling in this empty circle. That's what the standard non-parametric identification result is that a lot of studies rely on. But this is asserting unconditional parallel trends, which might not be credible because there's a lot of heterogeneity in the data. So later work basically said, let's use a propensity score. And the propensity score takes the same form as it did in the cross-sectional setting. And we use a reweighted version of this trend. So now intuitively, we're taking this figure and then we're saying, in order to construct this empty circle piece, we're going to use a subset of these untreated units, and we're going to upweight units that look a lot more like the treated units, and we're going to downweight units that look very different from the treated units. That's broadly what we're doing when we do weights. And the final version of the estimator has the same structure as you saw in the augmented balancing cross-sectional estimator, which is, again, this outcome model complemented with a weighted estimator. Okay. And finally, here's a full panel setting where you have lots of units and they're untreated for a certain number of periods, and then at some point, some subset of them get treated. So this is, again, a very standard setting that researchers in the social sciences and in industry deal with. So this is basically, this can be thought of as a generalization of the earlier two-period difference and differences setting. So differences and differences would be if we only observed some, like these two periods, where some of the units transition to being treated. Now, because we observe longer time periods before and after, we can, one, validate our assumptions, and two, estimate dynamic treatment effects. So we can actually estimate the treatment effect at each time period after the treatment kicked in. So here's an example of what that might look like. So here's a completely synthetic data set where I have 50 units and 50 periods, and 10 of them get treated at this dotted line point. And if you'll notice, the time series for each unit is contained within the envelope of all time series, which means that broadly speaking, the game is going to be to find units, find gray lines that look a bit like the red lines, and then use that to impute the missing potential outcomes. So that's broadly what a lot of panel data estimators are implicitly doing under the hood. So more formally speaking, the data here is an outcome vector and a treatment vector, and we're going to be in a setting what is called of absorbing treatment, which means that once you're treated, you stay treated. If you can switch in and out of treatment, things become a lot more complicated, and it's beyond the scope of this talk, but there's work going on that as well. So commonly used assumptions in this setting are analogous to the assumptions in two-period difference and differences. So we could assume that we have parallel trends between treated and untreated groups in this setting, but that seems somewhat extra strong, basically, because if it is the case that some subset of the units, some subset of the control units, some subset of these light blue units are good controls and a bunch of them are bad controls, difference and differences would weight them equally. And that could be bad. So we're going to let the data tell us the weights. So that's going to be the upshot of what we're doing in this setting. So when we assume parallel trends, we're assuming that the average in the treated units is parallel to the average in the control units. That might be not very credible in the presence of strong selection into treatment. So we're going to assume a somewhat abstract thing, but I'll try to expand on that in a second. So in general, an alternative to this long parallel trend setup is what is called a latent factor model setup. And what that means is that the outcome data, so here's a synthetic data set where there's no treatment effect. We're going to assert that the data is generated by a low rank decomposition. So units are allowed to have their own intercepts, and units are allowed to have their own time trends, but the structure of the time trends is somewhat low rank. What that means is there are units that are trending up, there are units that are trending down, there are units that are like poodling along stationarily. As long as we have lots of data, we can basically figure out which clusters these units belong to. And then for the red unit here that is trending very weakly positive, we're only going to use the units that belong in its cluster to construct its counterfactual. Similarly, for units that are trending downwards, we're going to put higher weight on control units that look like that. So the low rank decomposition assumption is basically an assumption about the structure of the potential outcome matrix. And in machine learning, people do this when they use recommender systems. Thus far, I haven't talked at all about Netflix because this was done before Netflix, but a large part of Netflix's work early on was to realize that people's tastes have low rank. Some people like action movies, some people like romantic comedies, some people want to watch, some people their tastes drift over time. But as long as the rank of the preference matrix is lower than the rank of the data, which is usually the case because we're not all that unique, we can decompose that into low rank components and then fill in the missing things. And the way that's used in machine learning is to do recommender systems. So, I could recommend you the next Mission Impossible movie if I know that you like action movies. The application in panel data is if you're one of these units that's trending down, I'm going to use other units that have been trending down to construct your counterfactual. Fundamentally, the low rank assumption allows us to fill in this matrix a lot more flexibly than assuming parallel trends. So this assumption underpins what is known as synthetic control, generalized synthetic control, matrix completion, et cetera, et cetera. And all of these works have been trying to relax the very strong assumption of using constant weights to construct counterfactuals, which is what parallel trends would require us to do. And the other potentially useful assumption, which again, I think in theory this could exist, but I have a harder time believing this could be true in practice, is that you could imagine that the treatment is as good as randomly assigned, given the history of your outcomes. And then we've reduced this to a cross-sectional problem. So if it is the case that conditional on the first 10 outcomes in your time series, your treatment is a coin flip, I can use those first 10 outcomes as covariates and then just do standard cross-sectional causal inference. So ideally, we want methods that are sort of adaptive to one of these two things being true. And my sort of opinionated view is that the second assumption is very rarely true, except when you actually randomize the treatment. So in general, I think the benefits from panel data largely come from this first assumption being satisfied by the data. And the way we're going to make progress on this is basically take all our time series data, so that blue matrix that I showed you, I'm going to take all the light blue elements. So I'm going to take every single light blue element here, and I'm going to try to fill in the light blue versions of this dark blue thing. So that's going to be the gain here, and that's denoted by a question mark here. So each row is a unit, each column is a time period, and I'm going to treat the pre-treatment outcomes as covariates. X0 for the pre-treatment outcomes for the control units, X1 for the pre-treatment outcomes for the treated units, and Yn for the post-treatment outcomes of the control units. So there are different ways we can tackle this problem now, given the setup. We can use synthetic control, which broadly speaking regresses X1 on X0, gets a vector of regression coefficients, and then predicts using Yn. So a synthetic control prediction for this question mark is going to assume that the relationship between the treated and control units is stable over time. and then use the weights that it learned on the complete data in the pre-treatment period to impute the counterfactual in the post-treatment period. Conversely, time series models are going to assume an autoregressive structure. So basically, a time series model would regress this post-treatment outcome on the pre-treatment outcome for the control units, and then use that to impute the post-treatment outcome from the pre-treatment outcomes for the control units. So that might also be reasonable. This is the sort of unconfoundedness given history approach. And some outcome models can fit both of these structures. So the low rank structure that I talked about earlier, if we directly try to fit the factors, we can, in theory, be agnostic about whether the horizontal or vertical regression is true. We can sort of adapt to that. And the particular, so this is belaboring the point I already talked about. The horizontal regression is the time series approach. The balancing approach is the vertical regression approach. And the augmented balancing estimator in this setting is going to involve both. So we're going to use a time series model to impute potential outcomes, and we're going to use weights to correct for potential biases in the prediction from the time series model. And the way we can do that is use a good outcome model that potentially learns both of these structures, and then we use this good set of weights to correct for misspecification, and that applies especially if we have very little data. So there are two famous estimators that already have the structure: synthetic difference and differences, which uses simplex regression for both. So basically it runs a ridge regression for horizontal and ridge regression for vertical, and it adapts between difference and differences and synthetic control in that particular way. The augmented synthetic control, I should have distinguished. So the simplex constraint here is somewhat important, and reasonable people disagree on how important it is. So a lot of the work done in the synthetic control literature has asserted that we want interpretable weights, which means that we don't want any weights to be negative or greater than 1. And we want weights to sum to 1, while when we run OLS, we see negative coefficients and large coefficients all the time. So we could either be agnostic to it, or we could enforce this interpretable weights constraint. So the difference between synthetic difference and differences and augmented synthetic control is basically how puritanical they are about this positive weights constraint. And again, that's an empirical question, and also depends on what you want to do with the results afterwards, because people tend to not like negative weights because it's kind of hard to think about. But I don't have any particular problem with negative weights. And the alternative that falls out of this, the results in this paper, is that we could use a matrix completion or factor model, interactive fixed effects model, that actually learns the low rank structure directly and use a different set of weights. Entropy weights are good because they they are non-sparse, for example. I said a lot of abstract things. Let's see some of these applications in practice. So this is the seminal data set that motivated a lot of synthetic control work. California passed Prop 99, which made it substantially harder to buy cigarettes. And if you did a vanilla difference and differences style analysis here, you would notice that the trends are far from parallel. So these are the raw averages in California and in every other state prior to the passage of Prop 99. And you will see that initially the gap was very small, and the gap started growing over time. So if we squinted at this, if we only knew difference and differences, we would be of the view that parallel trends doesn't hold. Sorry, let's put this in the file drawer and then move on. But when we think of this in this more general augmented balancing framework, we can make progress. So synthetic control basically says, I'm going to construct a set of weights that decomposes this red line into every state trend, and then construct a weighted average where the weights are positive and sum to 1 to track the blue line exactly. And when we have good data, that's pretty plausible. So it's completely feasible to do that. What synthetic difference and differences does is it says, I'm going to allow for level differences. So I'm going to allow for an intercept in the model. And then I'm going to try to track this trend as closely as possible. So the blue line, remember, is the line for California. So synth was saying, I'm going to make the red line sit exactly on top of the blue line. synthetic differences and differences is saying I can allow for level differences, but I want them to move as closely as possible. And then the imputed counterfactual is going to be the treatment effect. And another distinctive thing about synthetic difference and differences versus synthetic control based on this setup is that synthetic control relies entirely on these weights being good, while synthetic difference and differences and other augmented balancing methods are going to allow for the time component to enter more directly. So the jaggedy bit at the bottom is basically the set of time weights that the model learned. So synthetic difference and differences is putting greater weight on the time periods immediately before the passage of the policy, which seems eminently reasonable. While synthetic control implicitly, by running this vertical regression, puts equal weight on 1970 versus 1989, which seems suboptimal. So in every setting that I can think of that people use synthetic control, one could reasonably think that synthetic difference and differences is going to do a better job of like selecting the bit of the data that matters and then fitting the weights directly on that. So here's a figure that basically applies a bunch of these methods directly. So one final thing that I'll say, I hinted at this earlier, is that a lot of these estimators might look like nearest neighbors to you, and they are. So when you have lots and lots of data, you can actually just use nearest neighbors, and that's fine as well. So nearest neighbors is basically a discrete version of synthetic control where you pick, let's say, 5 units that most closely track the target time series you're trying to capture, and then we're going to estimate that. In this case, because we had limited data, it's biased. It kind of so the event study plot for difference and differences reflects the fact that we didn't have parallel trends. We had this diverging time series between the two. But when we construct non-uniform weights using a variety of methods, we get broadly consistent answers that are of the form that the treatment effect was between 10 and 15 percentage points. There are a few time series models that overfit, again, because we have limited data. And finally, for inference, I think inference in this time series setting is tricky, but in general, things like the bootstrap and jackknife are shown to work well in the time series setting. When you have only one treated unit, it's very hard to think about inference in general because it's non-standard. The proposal in the synthetic control literature has largely been to use permutation testing type approaches because you can't use the bootstrap because you can't. A given bootstrap draw might have no treated units because the treated unit, there's a single treated unit. So a lot of standard inference procedures need to be adapted to apply to this setting. Okay, that was a lot of notation, apologies. I'll just show you pictures. So I have a laser pointer, I'll use it. So here's a cross-sectional simulation setup. So this is an extension of a simulation study in Fröhlich and Heinmüller 2012. Jens was my advisor. This is combining a lot of his work. So when we have good overlap, a lot of these estimators tend to agree, even when difference in means is obviously biased because we introduced selection into the treatment. But when we have potentially nonlinear surfaces and so on, the augmented balancing methods and augmented IPW methods dominate a lot of other standard approaches that we would attempt in the cross-sectional setting. So we can continue. Well, the upshot is basically the same. I'll skip this in the interest of time. A much larger simulation study that I did was to use the 2016 ACIC DGP, where there are a very large variety of potential data generating processes for observational causal inference, which vary the functional form of the treatment and response, and the amount of overlap and the amount of treatment effect heterogeneity. And in general, we find that the balancing methods here are BAL-HD and augmented balancing. They have very good bias and RMSE properties relative to some standard methods like IPW and OLS. Okay, so moving on to difference and differences, I'm going to generate data where we either have conditional parallel trends or unconditional parallel trends. So when we have unconditional parallel trends, that vanilla picture that I showed you earlier holds true. So the true effect is the same as the difference in differences estimate. When we have conditional parallel trends, the naive difference in differences estimate is going to be badly biased. And I'm going to show you that that's going to be reflected in the bias and the absolute bias and the RMSE of the treatment effects. So when you have unconditional parallel trends, all of these things are good. IPW, because we're estimating these weights, actually might end up looking worse than vanilla difference in differences because we used a propensity score model, and the propensity score model could be quite bad. When you have a lot more data, I think the discrepancy kind of goes away. But typically in difference in differences settings, we might not have all that much data. When we have conditional parallel trends, the standard techniques are all biased, while these weighted estimation procedures do a lot better. When things are very, very badly misspecified, all bets are off. But even then, I think the bias and RMSE of these balancing methods tend to be lower than what you would get from sort of the standard approaches of difference in differences or IPW difference in differences. Okay, I'll skip this. And in the full panel simulation setup that I want to spend the most time on, I'll generate data that either has parallel trends or it has severe time trends, and it has an autoregressive structure. So basically, we're going to begin with a very favorable DGP for the difference in differences model, and then we're gradually going to introduce things that would break it. So time trends, unit-specific time trends are a very particular form of that low-rank assumption that I talked about. So this will bias difference in differences, but these other machine learning time series style models can pick this up. And autoregressive moving average models can have arbitrary sort of correlation across units and over time periods. So it's still low rank, but it's a lot harder to learn. And I'm going to pretend that the treated units are treated in the last period, but the true effect is 0. So implicitly, this basically boils down to estimating prediction error. So here's an example of a DGP where parallel trends is true. And here's an example of a DGP where parallel trends is obviously not true. So the weighting is going to do a lot of work when faced with a DGP like this. So here I'm going to show bias. Absolutely, this is basically a box plot of bias. And when we have parallel trends, synthetic control actually does worse than difference in differences because we're potentially throwing away the information that we have about parallel trends. So synthetic control might pick a small number of units to have positive weights, but the true optimal weights are 1 over n for everyone. So diff and diff does super well when parallel trends is true. And as we increase the amount of data that's available, and when we increase the noise in the data, the gaps between the estimation strategies don't change very much, but in general, synthetic control is biased when we have true parallel trends. But all these methods that can accommodate both time series and balancing methods, they are adaptive between diff and diff and synth. So in this case, because diff and diff is true, it's going to basically pick close to uniform weights and we're good. However, once we have non-parallel trends, diff and diff is really bad. It's going off the screen. Synthetic control is a bit better, but these adaptive methods do even better than pure synthetic control weights because in general, they're going to make use of the fact that they know that the data is persistent over time, and that's going to increase improve their performance relative to standard methods. And the basic story is true. When you increase noise, however, a lot of things go badly, but even there you have best performance from these adaptive methods. And yeah, so here I just increase the number of units. Similar thing holds true. And final simulation slide is basically under non-parallel trends with lots of units. I think these balancing methods really shine because they can pick weights from a lot of candidate donor treatment. Given, let's say, like 800 control units, difference in differences is going to put 1 over 800 for each of them, which is far from optimal when the data has non-parallel trends. So a lot of the benefits from using these weighting methods are when you have lots of potential donor units. Okay, One last point I'm going to try to belabor related to something I mentioned much earlier in the talk is that we said we penalize dispersion, and that's again a choice of loss function. So in a lot of standard approaches, this loss function is just the Euclidean norm of the weight. So synthetic control does this, and synthetic difference and differences does this. When we use entropy weights, however, using the entropy of a vector is equivalent to saying I'm penalizing deviation from uniform weights because the maximum entropy weights are 1/n. So entropy has this nice property where it interpolates between difference and differences and synthetic control nicely, because it's going to change difference and differences weights just enough to make parallel trends true. So empirically, I'll show that in a simulation setting where basically synthetic difference and differences has very non-sparse weights because of penalization. Synthetic control basically picks out a set of weights, a set of donor units, and it gives them positive weight and everyone else gets 0 weight, while entropy balancing has a much smoother decay. So in settings with small numbers of time periods, entropy balancing is a good choice, basically. I'll skip this, and to conclude, basically, the thing that I was trying to convince you of with this talk is that flexible models can be judiciously used for reweighting methods to improve the robustness of our estimates, our causal estimates to misspecification. And the general consensus in a lot of the causal inference literature is that adopting a hybrid structure that combines an output model with weights that target sample balance tends to do well. If either of these things is true, and if nature is unkind, our models are usually wrong. When both models are wrong, these augmented type estimators have better properties than betting your house on getting either the outcome model or the weights right. For future work, the setup that I showed you has this very strong assumption of contemporaneous treatment, which might not be true. And there's work going on that along those lines. Okay, and we proposed a common framework for augmented balancing estimators, and I'm going to release an R package called Aval, which should implement most of the estimation strategies that I talked about in the talk. Hope that was helpful. Open to questions. I didn't get any notation questions, I noticed, so I'm assuming people were either very clear or bored. So
no, thank you very much for a wonderful talk. I'll stop recording.